Hello and welcome. This is the first video in chapter 27. We begin our discussion of electric current with a qualitative overview of what current is. And by the end of this chapter, we should have a really good conceptual picture of how current flows in a metal. And so that's the specific material that we're going to stick to. Obviously, when you discharge a capacitor, with equal and opposite charge on both sides, what you're going to observe is that the charge had to travel through the wire. Right? This is the most basic idea. It didn't travel through empty space in between the plates. It traveled straight through the wire. And so what are some ways we can tell that charge actually flows through wire? Because unlike physics 1, we can't visualize electric charge. We can't see electric charge. We can only see its effects, the forces that are applied on it. And these are two other effects of moving electric charge. The first one being that heat is radiated out, right? This is your toaster, this is your electric stove, this is your light bulb, or this is even your laptop or smartphone that gets hot after too much processing power. So the heat that's radiated out is one big effect of electric current. The other one being that the electric current deflects compass needles. So there's some sort of magnetic effects that are created when electric charges move. These two effects will be studied in more detail in later chapters. And so when we restrict our attention to metals, we're going to only use electrons as the charge carriers in the metals. Again, we want to think about a conductor as a grid of positively charged atoms surrounded by a cloud or a sea or an ideal gas of electrons. So the metal literally has an ideal gas of electrons inside of it, this movable charge. And that movable charge in the metals, that's where we get our electronics, because we're able to move this tremendous amount of charge in these materials without the charge actually leaving the material. So it's able to just pass through certain regions, able to turn on a light bulb or charge something or store energy somewhere. That's the idea. And so to begin with, since electrons are the charge carriers in metal, we start by defining what's called the electron current. This is different from capital I, which is what we're going to call conventional current later in this chapter. Electron current is defined as the number of electrons that pass through a certain cross-sectional area of a wire versus time. Right? So how many electrons pass through a certain tube in time? And although that's the definition, we can kind of simplify it into more reasonable terms, because capital N is the total number of electrons that pass in that unit of time. And if we look at these pictures here, we see that the electrons in a certain unit of time, the electrons which have moved, now they cover this volume in this little dotted lined cylindrical kind of container here, this dotted line cylinder. And so the total number of electrons, capital N, is equal to a number density of electrons times the volume that's enclosed. And that volume is enclosed is, you pretty much assume that the size of the wire is constant. And when the size or the gauge of the wire is constant, then that volume is just equal to the cross-sectional area of the wire times the kind of wire distance that the electrons travel, which these pictures call delta X. And in a certain time of t, obviously, they travel a distance of speed times time. And so that's how we're able to go through this equality on the left hand of these slides here, to reduce the electron current, which we originally defined as total electrons over time, into these other quantities. The lowercase n is called the free electron density. It's the number of electrons per unit of volume that are available in that certain material. Right, cross-sectional area A is obviously how big it is, and drift velocity is how fast they're moving on average. And in this table, we see that most atoms only contribute 1 electron to the C. It's kind of it's really interesting that if you take, like, you know, if you can imagine just a bunch of copper atoms by themselves, you know, they're neutral. They're just a bunch of electrically neutral copper atoms. But when you form a solid, when you form them into a solid, their energy, the energy of the solid is lowest when every copper atom donates an electron to this whole solid as a whole, turning into this positively charged grid with a gas of negatively charged electrons floating around. And this is the formulas for electron density. It's worth mentioning that this quantity is not fundamental. As this discussion on the slide says, the free electron density, if you make the assumption, which is pretty valid in almost all cases, if you assume that the atoms all donate a single electron to the free electrons, well, then this free electron density is the same number as atoms per volume. And so to find that number, you have to know the density, the mass density of the material, right? With a simple mass, you know, inertial mass divided by total volume of the material. And you also have to know the molar mass, right? What's the total mass of, you know, an atom of copper, and what's the mass of, you know, 6.02 times 10 to the 23rd atoms of copper. You need to know those two. If you know those two numbers, then you can find this, you can calculate this number. So this number depends on the density, mass density of this material, depends on the molar mass of this material, and also Avogadro's number. So it's not a fundamental quantity, but we're going to treat it as such in the derivations that are coming. So this is kind of an interesting picture. This drift velocity that we've got, that you can imagine that in a wire, these electrons are drifting, there's tons of electrons, and they're drifting extremely slowly. We're talking like 10 to the negative 4 meters per second, right? A millimeter every 10 seconds, right? It takes, you know, so it takes almost 2 minutes, over 2 minutes for an electron to pass and to travel a single centimeter, right? And so if you consider a, you know, an average size wire that's maybe like a foot long or so, and that means it would take over half an hour, you know, 30 minutes, 20 minutes, 25 minutes for a single electron on one plate to travel the entirety of the wire to the other plate. And yet we observe that this discharge of these two plates is nearly instantaneous. It's almost a matter of nanoseconds that it takes for this to discharge. And so there's a disconnect there. And it's the same disconnect that you see, you know, in the atmosphere. It's the same analogy that you would make between thinking that, so when you say here someone popping a firecracker a mile away, that's this silly analogy here would be like thinking that the information about the firecracker popping would travel with the wind speed, right? Obviously, the information about the firecracker popping doesn't travel with the wind speed, it travels with the speed of sound. And the reason that these capacitors discharge almost instantaneously is that this information about this charge moving is what travels at nearly the speed of light, not the speed of the charge itself. And so you can think of this discharge as like, you know, the electron on the negative plate pushes the electrons next to the negative plate, which pushes the electrons near them, which pushes the electrons near them. And that push over all of them, that's what happens almost instantaneously. And this is the idea. This is the exact idea that we're talking about. But much like you need when you push a book or when you push a box across a hallway, you'll push it at a constant speed, but you're applying a constant force, so there has to be a resistive force. And in electric current, there's also an equivalent version of this electric force, of this resistive force. But it's the electric field that's pushing these charges along. The concept of electrical resistance studies and identifies this resistive force that's equivalent to friction. And we'll talk about that later. But let's return to this video of discharge, or let's return to this picture of discharging a capacitor. What you see on the right-hand side is you see these two positively charged plates, and they're both connected with their wires. And so each of these wires has same charge as the plates, but the wires aren't in contact. So when you connect them, here's the critical idea for understanding how electric current actually is formed. When you connect them, then again, almost instantaneously, within a matter of nanoseconds, there is what's called a non-uniform surface charge density that forms in these two wires now. And starting at the negative plate on the left, you're going to see a very large negative surface charge density on the wire near the plate that gets smaller and smaller and eventually goes to zero right in the middle. And then after it passes through the middle, you start to see a positive surface charge density get bigger and bigger until it reaches the charge density on the plates. And so that surface charge density that's variable and not constant, that creates an electric field inside. The non-uniform surface charge density always creates an electric field that points from positive to negative, or positive to less positive, or positive to zero, or zero to negative, or negative to more negative. That is the direction of the electric field that's created when the non-uniform surface charge density is imposed on the wire. So this is the important idea behind electric current. This is how we get electric current, because you have the electric field pushing the ideal gas of electrons, forward. Actually, it's actually in the direction against the field because they're negative charges, but this is how you're able to get electric current. And so that is how you're able to get electric current in a wire. But what's happening to the electrons themselves? This is the picture that we're able to study to get a picture of how the electrons are actually moving inside. And this will actually be the topic of the next video. I'm going to end this video now because we're starting a new kind of topic. So thanks for your time, and we'll see you at the next video. Take care.